Hi everyone. As you all know, PID type controllers are nothing more and nothing less than digital filters, which can be discretized, for instance, by using the backwards difference approximation or by using the Tustin discretization method. Well, this video does not discuss the different ways how to discretize a filter, but how it can be implemented after discretization has taken place, which has resulted in a discrete transfer function or in a difference equation. Well, there are a couple of implementation types. We have the direct form, the serial form, the parallel form, and the canonical form. And the discrete form as well as the canonical form are the two implementation types which are used more commonly. But we will also discuss the serial form and the implementation form. And when you are going to choose one of these implementation types, you might consider aspects and constraints with respect to costs, with respect to timing constraints, and with respect to output signal quality. When you think of cost, you might think of the amount of memory, for instance. There are a lot of videos and there's a lot of information on the internet about these implementation aspects and how they can be related to these implementation types, and we're not going to discuss these aspects related to these implementation types. So let's start off with the first implementation type, which is the direct form. And here we have a transfer function which we have called d, and d is a transfer function of a filter. Y is the output of that filter and X is the input of that filter. And we have described that in the discrete domain in the Z domain. And this is my example which I'm going to use, which has a numerator and a denominator. And when we work that out, we have in the numerator 1 minus 0.25 times Z to the power minus 1. And when we work out the denominator, we get 1 minus 1.5 times Z to the power minus 1 plus 0.5 times Z to the power minus 2. Remember, Z to the power minus 1 is a delay of one sample. So it's always good when you want to implement a filter to write these powers to a negative value, because the negative value can be realized by using delays. Z to the power minus 1 is a delay of one sample, so Z to the power minus 2 is a delay of two samples, and so on. So it's good to have this kind of an expression. So again, we have a filter with this transfer function, which says that y, the output of that filter, over x, the input of that filter, complies to this expression. So by using cross multiplication, we can say y times the denominator, so y times 1 minus 1.5 times z to the power minus 1 plus 0.5 times z to the power minus 2 equals x times the numerator, so x times 1 minus 0.25 times z to the power minus 1. When you work that out, you get y minus y times 1.5 times z to the power minus 1 plus y times 0.5 times z to the power minus 2, which is equal to x minus x times 0.25 times z to the power minus 1. And in words, it means that we get the following expression: y minus 1.5 y one sample delayed plus 0.5 times y two samples delayed equals x minus 0.5 times x one sample delayed. All right, so when we have that, we can say, when we have that cross multiplication worked out, we can say y is equal to 1.5 times z to the power minus 1 times 1 minus 0.5 times z to the power minus 2 times y plus x minus 0.5 times z to the power minus 1 times x. Well, that's in the z domain, but we can also express it as a so-called difference equation. In the time domain, we can say y is equal to 1.5 times y one sample delayed, which is written over here, minus 0.5 times y 2 samples delayed, which is written over here, which is that z to the power minus 2 in the z domain, plus x minus 0.25 times x 1 sample delayed, which is expressed over here. So now we have worked this transfer function out in a way that we get a difference equation in the time domain. And now we can build that filter, and we can do it as follows. We can say, well, we start off with the input signal, which is x, which is over here. And we have x, and we subtract from x the previous sample of x, which is written over here, which is in the z domain x times z to the power minus 1. That is written by this time delay over here, which is purely one memory block, multiplied by 0.25. And we have to subtract that value from that input value x over here, from this value. But we have also, in the end, my output, y, and when we delay that output, one sample, and we multiply by 1.5, which is in this branch, the multiplication of 1.5 and the delay of one sample over here, and we add that to the input signals, and then we have to use y, the output, 2 samples delayed, so I have one y delayed one sample, delayed another sample, multiplied with 0.5, and we subtract that from the rest what we have also over here, then we get the output y. So what you do is from a transfer function, you do the cross multiplication. First of all, you check whether this transfer function has been written with z to the power, which have to be negative powers, because they have to be delays, which we can implement as a filter. Then we do the cross multiplication, and we write that out as a difference equation. And then we start off with the input and with the delayed inputs. Then we draw the output, and we add to these inputs the delayed output and the delayed output, which is delayed 2 samples. So that is that expression. And then we add everything up with the correct signs, minus over here, plus over here, minus over there, plus over there, and then we get the output. Remember, I've written this as a difference equation in the time domain, which is not necessary, because we can also say we do the cross multiplication over here, and then we work this out with a z to the power minus 1, because we know that z to the power minus 1 equals a delay of one sample. And when you want to do this in Simulink, which I'm going to show you at the end of the video, Simulink asks for a block, which is a z to the power minus 1 block, which is the delay of one sample. So we can do it either in a difference equation in time domain or in a discrete z equation. All right, that is the direct implementation. Then we have the second implementation form, which is a serial implementation. And what we do in a serial implementation is that we work out the different parts in the numerator and in the denominator. So in the numerator, we have this expression, which is expression over here. Then we multiply that part with 1 over this part in the denominator, which is that expression, and we multiply it with 1 over this expression in the denominator, which is that part. And then we have 3 blocks in the total transfer function, three blocks with different input and an output, and the output of the first block is of course the input of the second block, and the output of the second block is the input of the third block, and the output of the third block is the output of my total filter. So we are going to build this in 3 blocks, and then we connect it in a serial or cascade way, and that's why we call this a serial implementation. First of all, let's start with this part of the equation, so with the first block. And it says that y equals, so the output of that block equals the input minus 0.25 times the input one sample delayed, which is, of course, because we have that z to the power minus 1 over here. So then we get this kind of block, with this kind of implementation, we have the input, which was this 1 times that x, and we have the input, one sample delayed multiplied with 0.25, which is this part, this branch, and then we subtract that branch, the minus over here, from the input signal over there, and then we get the output of this block. And this output is the input of that block. And for this block, we can say, well, the output of that block, y minus z to the power, excuse me, y minus z to the power minus 1 times y equals x. So we can say that the output of this block is equal to the previous output, z to the power minus 1 times y, plus the input, which is that input, times 1. So 1 times the input over here. And when we do that, then we have this kind of an implementation, which you can see that the output equals the input 1 times x. This is my x for that block, plus the z to the power 1 to the power minus 1. So the delayed output over here, we add that to this input, and then we get the output of the second block, which is of course the input for the third block. And the third block is an equal block compared to the second block, only we have a multiplication of the output signal times with 0.5, so multiplication of 0.5 in this branch. So when we do that, then we get this kind of implementation. So now we put all these blocks in a serial way, so in a cascade way, and then we have the serial implementation of that filter. So this is my serial implementation. Third implementation is the parallel implementation. And what we do when we use the parallel implementation, we are going to use the partial fraction decomposition to split this transfer function up and to split it up in first order parts. So in first order systems over here. Well, how did it work, partial fraction decomposition? Well, when you don't know exactly how it worked, please look to the appropriate video. And when you want to check whether this is the same to that expression, well, you can multiply the numerator and denominator with this denominator, and you can multiply this numerator and this denominator with that denominator, and then add up the numerators, and you should get this numerator again. So when you want to work that out, please do it. And when you're ready to see the rest of the video, please come back. All right, you're back. So you've done the you've done the partial fraction decomposition, and we have two parallel branches, two system blocks over here, which can be implemented in a parallel way. So we are going to make this system block, we're going to make that system block, and then we subtract that system block from this system block. So then we have, in this case, two parallel branches. So first of all, let's make this system block. We do it again, which we discuss in, for instance, the direct implementation method. We say that y times 1 minus z to the power minus 1 times y equals x times 1.5. Or we can say the output y equals the previous output indicated by that z to the power minus 1 plus the input, and then multiplied with 1.5. And then we get this kind of an implementation. So we see this, which is x, the input, plus the previous output, which was indicated by the denominator, and then the result multiplied with the 1.5 over here. Well, the second branch can be made in an equal way. So it's the same situation, except we have a 0.5 in that feedback branch over here, and we have to multiply the outcome with 0.5 instead of the 1.5 over here. So when we do that, then we get this implementation. We multiply it, as we said, with 0.5, and then we have to subtract this block from that block, and then we have the output. So that is the parallel implementation. Leaves us with one implementation form, which is the canonical implementation way. And the canonical way of implementing a digital filter is more or less a special way of implementing it in the direct way. And when we look to the direct implementation, we worked out this transfer function in this way. And we worked it out by doing the cross multiplication, and then we got this as a difference equation over here. What we are going to do now is we are going to take all the parts with the same delay from input and output together. So we have an input signal without a delay. Then we have an input signal with one delay, but also an output signal with one delay. And we have only an output signal with two delays. We don't have any input signal with two delays. And we group them together, and then we get this expression. So this is my input signal without a delay, which is over here. This is my input signal with one delay, this part, and we have the output signal with one delay, which was that part, and then we have left only the output signal with two delays, which is this part of the expression, which is written over here. What we're going to do when we are using the canonical implementation, we are going to reuse the delay of both the input and the output. And we work from right to left, working with different delays. So let's do it. We start off with the input, which is the signal X, which is over here. And we draw that input signal to the right of my implementation block. So it's drawn over here. We also have an input signal which is delayed one sample, which is written over here and multiplied with 0.25, and that is this part. So here we have X multiplied already with the 0.25, and we are going to use to implement the delay afterwards. But what we also see is that when we have an output, we have also a part of the output which is also delayed one sample, which is this part of the equation. So that's why I've drawn the multiplication block, the 1.5 underneath the 0.25 of the input block over here. So now we are going to realize this part of the difference equation. So I'm going to add the input signal to this part of the combined input and output signal, which are delayed one sample. So this is my input signal delayed one sample. Here's the minus. This is my output signal, one sample delayed, multiplied with the 1.5 over here, with the plus over here. And now we're not going to use the delays in these branches and these branches, but we're going to use one delay in which we are going to implement the difference of the input and the output. And we add that to the input over here, and then we get this part of the difference equation. Now we have to implement only this part of the difference equation, and we see over here that we have to delay the output signal twice. So we have to take not the previous output signal, but one signal further, so two delays, multiplied with 0.5, and we have to subtract that from the result we had already. So here we have to have a minus over here, and you can see that I implemented a delay in this branch, which is one of the two delays which I need, but I'm going to reuse the delay which was already used in this part of the equation. So now I get an optimal form in which we reduce the number of delays, because again we are using this delay for the two delays which we have to use in this part of the equation. And the second delay for this part of the equation is a reuse of the delay which we use in this part of the equation. And again, that delay is a combined delay for the input signal and the output signal. So the canonical way is a way of implementing a filter with respect to the reduction of the use of memory. Well, this is a kind of presentation. Well, let's have a look to Simulink, how you can implement it in Simulink. I'll put this presentation away. I'm going to open a blank Simulink drawing over here. When you're going to look to the Simulink library, you have to use the discrete library. And when you want to use a delay, you can, for instance, use a unit delay, which can be drawn over here. And when you draw it in your model, you see when you double click on the block, one moment please, there it appears. You see here it is a unit delay. When you double click on it, you see that you can fill in the sampling time, which is here -1. -1 stands for inherited from another part of your from your system. But when you want to fill in a specified sample time, you can fill in, for instance, 0.001 when you want to have a delay of just 1 millisecond. So in that case, my sample time is 1 millisecond. So one delay equals a delay of 1 millisecond. Well, that is a delay. And when I want to delay it, for instance, 10 times, I can put this part 10 times in cascade or in series, but then you get not a very useful schematic drawing. So what you can use then is, for instance, a delay over here, in which you can specify the number of samples which have to be delayed. This is z to the power -2, and that -2 has been written over here, a delay length of 2, but when I change that, for instance, to 10, you see over here that it changes to z to the power -10, which is equal to 10 blocks, 10 unit delays in cascade. So don't forget also in this a block that you write down its sample time. And of course, when you want to add these up, you can go to the math operation block, and then you can go to the subtract or the summation block, and you can add it all up, etc. Well, that's all about filter implementation in a discrete way. Thank you for watching, and I see you next time.